In the last video we set up the differential equation that models a mass undergoing oscillation. This term is the resultant force on the mass. This Newton's second law, F equals ma, mass times acceleration. This term here is the force on the mass due to damping or friction. That force is proportional to the speed. The speed is the magnitude of the velocity. Also, this force is in a direction opposing the velocity of the mass. So the direction of this force is opposite to the direction of the velocity. And this term here comes from Hooke's law. This is the restoring force of the spring. So this force is proportional to the displacement of the spring. That's the magnitude of vector x. And also this force is in a direction opposite to vector x. Here is the auxiliary equation. We use the letter lambda instead of k. We use k in previous videos. Well, that's because k is actually appearing here. So in order to avoid confusion, we use a different letter. The auxiliary equation enables us to get solutions of this homogeneous second order differential equation. We know the solutions of this differential equation involve the solutions of the auxiliary equation. So we solve the quadratic to get this here. And in particular, the solutions of the differential equation depend on the nature of this discriminant, well, the nature of the roots of the auxiliary equation. Now in this video we are going to consider the case where k is not 0. In the last video we set k equal to 0, so this term just disappeared and the k's disappeared here. So we're not going to do that here. So k is some non-zero number, and we are going to consider the case where the discriminant is negative. We'll start with that case. So we will have complex values for lambda. Now we can write k squared minus 4mn as minus 1 times 4mn minus k squared, and then we can take the square root sign over each factor. So we'll have the square root of minus 1 times the square root of 4mn minus k squared. Well, the square root of minus 1 we call I. So we get two solutions depending on whether we take the plus or the minus. So we will call the two solutions lambda 1 and lambda 2. Now, we saw from a previous video that if the auxiliary equation has complex roots, alpha plus beta I and alpha minus beta I, then the solution is given by this here. So we have e to the power of the real part of each complex solution. Well, the real part is minus k over 2m. And that's multiplied by the independent variable. Now it's x here in general, but the independent variable here is t. And then we have a times cos of beta times, well, not x but t in this case. Beta is the imaginary part of the complex. It's actually the magnitude of the imaginary part. So that's the coefficient of I, root 4mn minus k squared all over 2m. So that's what we put in for the coefficients of t. T is the independent variable here. Now we're going to give specific values to m, n and k. So we set them all equal to 1. We are going to find lambda 1 and lambda 2, and from lambda 1 and lambda 2 we are going to get the solution of the differential equation. So if we put k equal to 1 and m equal to 1, the real part will be minus 1 over 2. The real part will be minus a half. So that's what we have here. And inside then we have 4 times 1 times 1 minus 1 squared. Well, that's going to be 4 minus 1, which is 3. So we get root 3 over 2 for the imaginary part. So the general solution for this differential equation is given by e to the power of the real part times t. Well, that's minus a half times t. A cos the magnitude of the imaginary part times t. Well, the magnitude of the imaginary part is root 3 over 2. So that appears as the coefficient of t. Next we have these initial conditions. Suppose that the position vector of the mass is x0 at t equals 0. So this is the initial position of the mass. And suppose the mass is released from rest, so its velocity dx dt is 0 initially. So we'll start off with dx dt, so we need to differentiate this, set it equal to naught, and then plug naught in for t. Now we've a product of functions of t here. So we differentiate one function and multiply it by the other. So if we differentiate e to the minus t over 2, we'll get minus a half e to the minus t over 2 by the chain rule. And then we multiply by this, so we just copy this down. Then we take e to the minus t over 2 and multiply it by the derivative of what's inside the square brackets. We differentiate cos, we get minus sine. And we multiply by the derivative of root 3 over 2 times t, which is root 3 over 2. The derivative of sine is cos, and we multiply by root 3 over 2. We set t equal to naught. Well, the sine terms will disappear. Sine of naught is naught. So here we'll have the cos of naught, which is 1. And over here we have the cos of naught, which is 1. So this is what we'll get, and we set the x dt equal to naught. Now you see we can divide across by e to the minus t over 2. So we get minus a half a plus root 3 over 2 times b equals naught. Now we also know that x at time 0 is called x sub 0. So we plug 0 into this, so we get e to the power of naught, which is 1. The cos of naught here is 1, so we get a. The sine of naught is naught, so we just end up with 1 times a, which is a. So x naught is equal to a. So we found a. A is the initial displacement vector of the mass, and we plug x naught in for a here and solve for b. So this is what we get when we plug x naught in for a, multiply all the way across by 2, and we get, and shift over the x naught, we get x naught equals root 3 times b. So b is x naught divided by root 3. Now for some reason b is written like this. We can multiply above and below by root 3. Root 3x naught over root 3 times root 3. Well, that's just 3. So we go back to our general solution. We plug x naught in for a, and we plug root 3 over 3x naught in for b. And we can pull out the x naught. So we will have cos root 3 over 2 times t plus root 3 over 3 sine root 3 over 2 times t. We get this here. Notice that the displacement vector will go to 0 because of the exponential term. As t gets larger, e to the minus t over 2 is going to head towards 0. So we'll end up with 0 times whatever's in here. So we'll end up with 0 eventually. So x is approaching 0. But we will see some oscillation from the sinusoidal terms in here. Okay, let's look at the graph. So the bold graph is our solution. Now this dotted graph is the solution for the case where lambda has only one value. So let's go back and look at that. So here are the roots of our auxiliary equation. So as a reminder, these are the roots. Now if k squared minus 4mn equals 0, then we saw in previous videos that we only have one root of the auxiliary equation, and it's going to be minus k over 2m. So we just have one root, or this one root is sometimes referred to as two equal roots. And here's the solution. This is the form it takes. Now we have different notation here in this video, so I'll just adopt it for the notation we are using here. The dependent variable is x here, and so we have x of t equals a plus b times t times e to the power of, we're not calling the solution of the auxiliary equation k, we're calling it lambda here. So we've lambda times t, e to the lambda t. Here are the initial conditions for the problem, and we're going to plug these in. So when t is naught, x equals x naught. So we replace x with x naught. We replace t with naught, so that term goes out. And e to the power of naught is 1. So we get x naught equals a. Next we get dx dt. We will set that equal to naught at t equals naught. So we have a product of functions here. So we take one function, say the first one, multiply by the derivative of e to the lambda t. Then take the second function, e to the lambda t, and multiply by the derivative of a plus bt, which is b. And we want to set this equal to naught when t is naught. So we plug naught in for t. So we get a plus b times naught times lambda e to the naught. Well, that's just going to give us a lambda. And when t is naught here, we get b. And we want this to equal naught. We want dx dt to equal naught. We've already established that a is x naught. So that's equal to x naught lambda plus b, which equals naught. We can solve this for b. So we solve for b, and we get b equals minus lambda x naught, and plug in for b here. And we know that lambda is given by this thing here. And actually in the example we're doing, both k and m are equal to 1. So this is minus a half. Anyway, for the critical damping case, we will end up getting this solution here. I plug minus a half in for lambda. Now x will go to 0 as t goes to infinity, because this term dominates. This will go to 0 faster than 1 plus a half t goes to infinity. Now the dotted graph here shows the critical damping solution for different initial conditions. So I calculated it for the initial condition that the mass is at rest, dx dt is 0. If we don't have that condition, we get a slightly different form here. But you can see that we do have x0 multiplied by e to the minus t over 2 appearing in the graph, x0 e to the minus t over 2. It's just, in this situation, the derivative at x0 is not 0, as you can see. The tangent to the dotted curve at 0 is not horizontal, whereas for the solid curve, the solution to the light damping case, the tangent is horizontal. So for light damping, k squared, that's the damping coefficient, is less than 4mn. But for critical damping, k squared is bigger. It's equal to 4mn. So we have a larger value of k, giving a solution that looks like the dotted curve. So we don't even have an oscillation. We can see that x is always positive, actually, assuming that x naught is positive. That's what we're assuming here. So we have no oscillation. So the mass just dies down to its equilibrium position, which is at 0. For higher values of k, where k squared, or sorry, lower values of k I should say, where k squared is less than 4mn, so we have lower values of k, so we have less damping, we see, well, a little oscillation. The mass goes through its equilibrium position, goes below its equilibrium position, and then back up again, goes above it, and then the motion dies to 0. So just to recap again, the damping term in the differential equation modeling the motion of the mass is k times dx dt. The bigger k is, the greater the damping. If k squared equals 4mn, we have what's called critical damping. We have just one solution to the auxiliary equation, and that means we have a solution of the differential equation that involves no oscillating terms. It involves a decaying exponential, so we see no oscillation. For k squared less than 4mn, so this k for the light damping is less than the k for the critical damping, we do have some oscillation. But because e to the minus 2 t over 2 appears, eventually the motion will die down to 0.